Hi everyone, so here we're going to talk about metamorphic rocks, and this is a little bit shorter because really only here we're talking about stresses and strain that exist in rocks as they're being altered by tectonic forces. And so you can imagine we take a igneous rock or a sedimentary rock and we start to push it into a mountain belt in a continent to continent convergence, or we start to subduct it in a oceanic to continent convergence or an oceanic to oceanic convergence. And that will change those rocks because new heat and pressure are being exerted on them. And so it changes the way minerals behave, the way minerals are aligned, the way minerals group up. Because with metamorphic rocks, we're really talking about a process, not really with all rocks, we're talking about processes. But in this one, we're thinking mostly about how do existing rocks on the surface become altered by tectonic events. So to understand how metamorphic rocks are formed, I'd like to return very quickly to the rock cycle again. And here we see our igneous rock formation either through intrusive or extrusive processes. And thus those rocks become exposed to the surface. We also have those surface rocks being weathered due to interactions with the atmosphere. And that creates sediment that then is transported through water and air processes. And that stuff gets deposited as sedimentary layers that eventually lithifies to sedimentary rock. And the metamorphic rocks that we're going to talk about in this lecture are really formed at the boundary where tectonic plates are interacting with one another. And we see that most intensely at convergent boundaries, where there's lots of pressure and lots of heat being generated as these things are smashing together, on huge scales. And so metamorphic rocks generally form in areas where you have tectonic convergence, and this changes the rock or alters the rock physically or chemically. But it doesn't melt the rock all the way, because if it did, then that would become magma again and would eventually cool to igneous rock. So these are rocks that you can imagine are on their way to melting through tectonic processes, but they get interrupted. And then they're preserved, in the geologic record. And that preservation shows us something about the tectonic forces that were being exerted on that rock at the time. So the main takeaways here for metamorphic rocks are that they form at high pressures and high temperatures, usually down here at some depth, right? Because they need to be stable enough as solids that they don't melt all the way into magma, and we need pressure for that, right? You can heat up a rock and melt it, but you need the pressure to keep it from melting, so it kind of becomes like the mantle rock that we've talked about, where it's really hot, but it's also under a lot of pressure. And so it doesn't melt all the way into a liquid. It becomes kind of this melted plastic kind of material. And as forces are being exerted on metamorphic rocks, that plastic material, so to speak, can be altered, right? The mineralogy can be altered. It can be folded. It can be just kind of all mixed up, right? And metamorphic rocks make up the kind of stable core or the interior of all of our continental plates, because you can imagine these are the first rocks that formed. Maybe they were igneous rocks, obviously at the beginning, and then they maybe get weathered and they're sedimentary rocks. But then as plates begin to interact with one another over time, it forms the metamorphic rocks. And so most of the cores of all the continental plates have been around a long time. They're like a 90-year-old man with lots of tattoos and lots of scars. They've seen it all, right? They've been through all kinds of different tectonic experiences. And so those scars show up basically as metamorphic structures or metamorphic features. And the key definition here is that metamorphism occurs when a rock is subjected to those environmental conditions like tectonics, and it alters it into a rock that is unlike the rock that came before it. So it tells us something about the conditions on the surface of the earth. If you have a igneous rock that formed as a pluton, say a granite, and it gets exposed, it's uplifted and exposed to the surface, and it's a granite rock face. Eventually, when tectonic forces start to act on it, that'll change the mineralogy and the different textures of that rock. And so that tells us that at one point in time in that one location, it was tectonically quiet, but it was volcanically active, right? Because volcanic rocks were being formed, or igneous rocks were being formed. But then something else happened at that spot, namely tectonic forces. And so the appearance of a metamorphic rock in the rock record tells us that the conditions at that one spot were changed. And we know that through the texture and the mineralogy changes that happen in the rock. So to understand metamorphic rocks and the process of metamorphism, I like to think of the following analogy. Let's say you're a car company in Germany. You have German employees, you have German designers, you source German products to build your car. You have a certain look and a certain feel to that car. We would call that a Volkswagen, right? And the same would be true if you were an American car company, sourcing American products to build your car. Americans are building the car. It might be a Ford or a Buick or something like that, or a Chrysler. And then you get your car out on the road and you start to interact with other cars and other people. And so you might be parked in a parking lot and you might get a minor fender bender, and that leaves a small dent in your car. Or you might total that car, not to be dark, everyone was safe, don't worry about it. You might total that car and then it's completely destroyed, it's completely smashed, right? And that's because of the interaction of that car with other cars on the road. Similarly, rocks like this shale here, or this granitic diorite or granodiorite down here, they form and have a certain look based on where they formed and how they formed, right? This was transported from sediment. This was sediment being transported from weathering and deposited elsewhere and turned into rock. This was a slow cooling magma that as part of an intrusive body. So this is our Volkswagen and our Ford here, right? But then these rocks are exposed to the surface, i.e. they got on the road and they interacted with other rocks and other forces, namely tectonic forces. And that altered the rock. Here's our fender bender here. This is kind of a low grade metamorphic rock. It still looks like your car, just has a dent, right, on the bumper. Or you can have high grade metamorphism where it really alters the rock and makes it look way different, right? And in the case of this granodiorite, it's been metamorphosed through strong compression, right? This would be your big kind of car accident. And it forms a metamorphic rock that doesn't look anything like this. It's made up of some of the same stuff, but that stuff has been compressed and folded and bent and changed in some fundamental way. And the way that these rocks are altered occur in two major metamorphic settings. We can have contact metamorphism, and that's when these rocks are touching or near a mass of magma. So those intrusive bodies that were coming up to form igneous rocks, they're obviously very hot, they're liquid. They're going to heat up or change the rock around them. And that's through the process of heat directly from the magma, or from that magma heating reactive fluids like water that exist in the ground or in the crust. And so that's hydrothermal. So that's a slightly different process from just direct heat from the magma. That's hydrothermal fluids, so superheated water moving through those rocks and altering them as well. And then we also have the one I've been talking about, which is tectonic forces acting on the rock as pressure and altering the rock through differential force. So that's force in just two directions, not all four, although sometimes all four directions. You can have pressure, like imagine squeezing a piece of Play-Doh with two hands as opposed to squeezing a piece of Play-Doh with one hand, right? If you squeeze a piece of Play-Doh with two hands, you're confining it into a ball and it's just shrinking in size and getting more dense. Or you could squeeze it with one hand where you're exerting force basically in two directions and then it shoots out above and below your hand. And when it does that, we call that differential stress. And this is regional metamorphism. Okay, so this is what happens at convergent boundaries, where different pieces of crust are pushing together, and it's exerting a force on the rocks stuck in the middle, and the rocks that are kind of away from the middle too, because the whole thing is kind of being altered, but more intensely at the boundary and less intensely away from the boundary. And this differential force we call regional metamorphism. And so the agents of this metamorphism are, again, like I said, heat, pressure, which is stress, and chemically active fluids, so hydrothermal fluids. And again, as the intensity of these agents increases, we get higher grades of metamorphism, right? So the intensity of someone backing into your car at Meyer is going to be different than your car flying off a cliff. And anyway, I'm going to abandon this analogy because it's starting to bum me out too. But you get the point. It's basically that different stresses produce different amounts of pressure, heat, and then if there's chemically active fluids nearby, they're also going to affect this rock. So the main driver in metamorphism is heat, and it's by far the most important metamorphic agent here, because once you introduce heat into any kind of a system, whether it be a solid, a liquid, or a gas, it begins to energize the atoms present in that system. It vibrates them. It produces different energy levels. And so that allows electrons to bond in different ways. And so what we start to get is different bonds begin to form between different atoms. And so we can get different minerals crystallizing and forming. And because it's a sustained heat over time, it allows new minerals to grow, similar to the way minerals grow in a magma chamber. But again, here I want you to remember that we haven't gone all the way to the liquid phase yet, right? It's an interrupted journey to that liquid phase. And so the rock is getting heated up and it's beginning to move like a liquid, but still a solid. So like a melted plastic, or like you could think like cold honey or something like that. And that can change the structure of the rock, but can also change the way that certain minerals are bonding within that rock and can grow new crystals, basically. And because of the different properties of different minerals, the lower temperature minerals like quartz and potassium feldspar and muscovite, they'll start to slightly melt and form new bonds and will thus recrystallize into higher temperature minerals. So it takes a quartz, it heats that quartz up to a point where it's liquid almost, right? And then that metamorphism stops at a certain point, so the heat stops being produced through that interaction, and it will then cool that partially melted quartz into some new mineral, like a garnet, let's say. And again, in order to increase the heat around a rock, you either have to have the intrusion of a magma body, or you need those rocks to be thrust into higher temperature zones through tectonic processes. And this can be burial, in the case of a convergent boundary between two continental plates, where those rocks are just being buried in the bottom of a mountain mass that's being formed from that collision, or through subduction, where oceanic crust is being forced down deeper into the crust and eventually into the mantle, which also produces the heat necessary for this process. So if you're heating up rock by heat alone, so no tectonic forces at all, what you begin to get is a recrystallization of the grains in a sandstone here, for example, and that forms a harder rock called quartzite. So what's happening there? Well, if we take this rock and we glue it onto a glass slide and we shave it down to the width necessary to shine light through it, and then we look at it under a microscope, if it was a sandstone, it would just be nice round grains and they'd be cemented together by some finer grained clay materials. And you just see nice orderly round grains in that microscope slide. But if you start to heat that rock up, similarly to the way we fire a clay pot, let's say, where you have just clay and water, and you're on your potter's wheel there doing your thing, and you make the pot, you put it in the oven, that's what cures it and hardens it. And that's exactly what's happening here. The grains of cement and the nice round grains of quartz that would have been in the sandstone slightly melt and form these larger grains. And you can see that they're in like kind of irregular sizes and also irregular shapes. And what's happening here is these grain boundaries are beginning to bulge into other ones. They're starting to change. So you don't have that nice, even, round sand grain. Now you have this kind of weird mass of silica, and we call that a quartzite. And it's just a harder rock where the grains are no longer necessarily present. It gives it this kind of sugary look in hand sample. And then we have pressure and stress. So due to tectonic activity, you can get different tectonic stresses that act on a rock in a given location. And what that tends to do is compact that rock and increase its density. But it also develops something we call foliation. And I've included this picture here because this is basically how to think about rocks that are foliated, where you have mineral grains within a rock, and we can think of those like the pages. And as those mineral grains start to heat up and get compacted, they also, if it's differential stress, they start to slide past one another. And you can do this if you just have a book in front of you or a notebook. If you just take the edge, not the bound edge, but the open edge, and you just bend the side of your notebook up, you'll see that the pages slide past each other. And as you bend it up, like in this picture here. And that is what minerals are essentially doing in a rock as they're put under pressure. And increasing the load above rocks by burial, we call confining pressure, and that's force applied equally in all directions. So that produces compaction. And then at plate boundaries, we get differential stress. And that's where you have unequal forces, like I talked about with the Play-Doh earlier, if you were squeezing Play-Doh with one hand. And that gives us differential stress. And here's a diagram that shows confining pressure pretty well, I think. You can imagine a sedimentary sequence here of different mudstones and sandstones and limestones and stuff being laid down in some marine environment. And when that, we could take a snapshot of that, a layer up here, and it would look something like this. It would have, layers of sedimentary rock, and it would have a certain volume, right? But once that gets buried more and more and more, say down here, now we have the same sedimentary layers in the same relationship to one another, but the volume has changed, right? These aren't folded. These are just being buried. So there's no fold. Everything's still horizontal. But now the volume, basically the pore space within that sedimentary rock, has decreased. And this gives us a higher density rock unit than we had when it was existing up here, closer to the surface. And that's confining pressure, which increases as burial increases. For differential stress, we can imagine a convergent plate boundary here, right? This is a continent-to-continent convergent boundary. Think like the Himalayas. And here we have stress only in these two directions, and we have no stress really up top here, and even less stress below, because these continental plates are moving together at much more force than anything that's coming from above or below. And so preferentially, this material is going to want to move up or down relative to the stresses on the side. And as that happens, you get undeformed strata up here, or the original sedimentary strata or sedimentary layers that begin to look like this. They're all folded and bent. And, that's just, I think I said it to you guys before. If you just take a rug on your kitchen floor and you push it in one direction, it's going to bunch up. And that's because there's more stress from your hands pushing than there is from the stress of the atmosphere, right? So it's going to preferentially want to move up because things always move from areas of high pressure to low pressure. And this is differential stress, and this is what we have in the base of mountains, and this is what gives us those folded, banded rocks that we have in our kit, namely gneiss. So the mineralogical or textural changes in these rocks are very different between confining pressure and differential stress. So in confining pressure, let's say we have a granite here. If we start to squeeze that granite down, it's just going to get smaller and more dense, but the alignment of these minerals isn't going to change much. They're still going to kind of be in the same alignment as they were before, but just more closely packed together. So that's confining pressure. If we have differential stress, if we were to take that same granite and we were only to squeeze it on the sides here, these grains would slowly begin to align this way, right? Because the majority of the mass of this grain wants to be aligned with the area of less pressure. And I did this demonstration in lab for a couple students, and I'll do it again in the upcoming lab. But if you just take a piece of Play-Doh, like a ball of Play-Doh, and you just stick a bunch of pennies in it randomly, imagine if you squeezed that Play-Doh from the sides, eventually those pennies are going to start to align perpendicular to the pressure that you're exerting on it. And when that happens, we get mineral grains that start to align like this down here, where they're now in these banded straight lines here. And this is foliation, but it's foliation from confining, or not from confining, from differential stress on either side. And so when you see a metamorphic rock like this, you know in its ancient tectonic environment where it formed, the pressure was coming from the sides here. And then we have hydrothermal fluid. So hydrothermal fluid is just groundwater in the crust that's heated up. And it has ions in it. It has different dissolved atoms in it, different, magnesium, silica, iron, whatever. That gets dissolved because it's heated up. Imagine just, dissolving sugar in hot water. Then that fluid begins to move through the sedimentary layers near a magma body that heated up that fluid. And as a result, we can get recrystallization of different grains in like a quartz sandstone or a limestone or a shale. And we can get new elements from that hydrothermal fluid, that heated water. more elements can go into and be incorporated into that resulting rock around the magma body. So with limestone, that gets heated up, sort of baked in a way. You can think about it like that. Maybe baked with steam, I guess you could think of it like that. And that produces a marble right around the magma body in that layer. And then like say a quartz sandstone layer just below it, around the magma body, you'd get quartzite. And then around a shale, in this layer here, we get something called a hornfels, which is not in your metamorphic rock kit, but I thought I'd mention it here because it's super duper common in metamorphosed sedimentary rocks. And so this is overall what we call contact metamorphism, where there's no tectonic stresses. This is just being heated up by hydrothermal fluids in this case. So in summary, metamorphic rocks change density. They usually cause an increase in density. You get the growth of larger crystals. You get the development of foliation, right? When there's differential stress and those rocks are beginning to shear. And you get a transformation of low temperature minerals like a quartz to a higher temperature mineral like a garnet, okay? And this is sort of the sequence here for foliated rocks. In your kit, you have a slate, that's your least metamorphosed. Then you have a phyllite, so it's starting to foliate a little more. Minerals are beginning to align and group up. Then you have a schist, which is even more foliated. Minerals are even more beginning to recrystallize and group together. But it's not until we get to the highest grade metamorphic rocks, here this gneiss, where all of those minerals begin to align in a standard direction based on pressure. In this case here, this gneiss, the pressure is coming from the top and from the bottom because we see the minerals aligning side to side here. And so you can think of a slate and a phyllite in this way. A slate is really formed from a mudstone that gets buried deep enough under confining pressure that it begins to slightly be foliated, but it's mostly just losing volume from its original mudstone. Phyllite, maybe we have a little bit of tectonic stress here. A schist, we have even more tectonic stress. And then a gneiss, we have the most tectonic stress with those grains being aligned that way. And then we can also have non-foliated, and that's the contact metamorphism I mentioned in the last slide. And here we have our marbles being formed from limestones that have been heated up by hydrothermal fluids. We have quartzites, also a sandstone in this case, being heated up by hydrothermal fluids. And then here's our hornfels or shale that was heated up by hydrothermal fluids. And these aren't foliated because they don't have any tectonic stresses on them. There's no force pushing on these rocks that align any of the grains in any particular way. And I'll point out, you can have a schist that was originally from a limestone, but because it had tectonic forces on it, that limestone started to have grains recrystallizing and forming in some kind of a pattern. Maybe even to the point of being a gneiss. The same with sandstones and the same with shales. You can get those to a point where they get to this what we call schistosic point, right, where they begin to form a schist. Generally with gneisses, though, gneisses are usually igneous rocks that have differential stress on them. And the reason we see the banding of these different minerals here is because you would need enough mineral growth in, say, a granite to produce the minerals available to be aligned in any direction at all. Whereas with sedimentary rocks, because they're so fine-grained, they tend to only reach the schist phase. And when it comes to differential stress, that is stress being applied to a rock in certain directions and not in others, we tend to get cleavage. the same way we get cleavage in minerals, where they cleave along zones of weakness within the crystal structure of a mineral. In rocks, we get cleavage along zones of weakness in the mineralogy of the rock itself. So certain minerals are going to be weaker than others. A mica is weaker than a plagioclase, for instance. And so rocks, when stress is exerted on them, they'll fail at certain areas where there's more mica, let's say, or more quartz or more biotite or something like that, as opposed to some of the stronger minerals. And so that's what's really producing the foliation. And so therefore we have different foliation textures based on the amount of stress being exerted on the rock. So for slates, we have slaty cleavage. And here you can kind of just break the rock up into kind of, planar flat surfaces. Like you can take a slate and you can kind of just pull it apart. With a phyllite, the grains start to coarsen and the rock will develop this shiny luster. And you'll see in your rock kits, the slates tend to have kind of flat planes on it. Looks like a cleavage plane. It's not as shiny as a cleavage plane in a mineral, but the same thing is basically happening there. Whereas phyllites, it starts to get real shiny. Those mica grains are starting to really align on the outside of the rock. And so they tend to have a shinier luster, and they tend to start to get a little bumpy, or start to have little kind of ripples in them. Then you can have a rock that kind of looks like fish scales, where the mica grains have really started to recrystallize on the outside. And they look like, literally flakes of mica and other kind of platy minerals. And that's what differentiates a schist. And then if you have a gneissic texture, that's, like we see in the gneisses. And that's where you get those true bands of minerals. And you usually have the dark ferromagnesian minerals separating out from the light felsic minerals, or non-ferromagnesian minerals. And that's where you start to really see a differentiation in the mineralogy, and it makes that striped, sort of banded look. And it's almost always folded. It doesn't have to be, depending on how far the sample zooms into the overall fold structure. But that's the idea here, that the gneissic texture is the most stress being pushed on a rock. In order to get that gneissic texture, the resulting rock is a gneiss that's usually folded, but it's always banded. And here's what that slaty cleavage looks like in a slate. And you can see here we've just got, flat sort of planes, and the rock would break up on those planes. And if you look at it on the top, you just see kind of a big, flat, broad area. But if you look at it on the side, that's where you start to see the lines. It almost looks like layers. And that's the slaty cleavage that we're talking about. And you can imagine just taking a stack of lined paper, or printer paper even. Imagine you just have a stack of paper, and then you just put your hand on the top and you just push in one direction, and you'll start to see that the pages are sliding past each other. And that's what's happening here. Then you have phylitic texture, as in in a phyllite. And that's where the grains coarsen and the rocks begin to develop this kind of shiny luster. And you'll start to see cleavage here beginning to happen in the plane up here that was broad with no cleavage. Now you're starting to see cleavage happening there. And that's because the rocks are not just sliding past each other horizontally, but they're starting to slide past each other vertically as well. Then you'll get to a place where the rock has this kind of scaly appearance. That's the schistosity. This is what a schist looks like. It's in your kit. It's the third metamorphic rock in your kit. And it's usually kind of a mess, right? It doesn't have, real defined planes of cleavage. And that's because it just has a whole lot of planes of cleavage. And then you have a gneissic texture. Here's a nice banded gneiss here. And here we can see that all the minerals have begun to align perpendicular to stress. So stress would have been happening from the top and bottom here. And here we see the minerals start to group together and separate different densities out from one another as a result of pressure, but also from heat, because those grains need to be able to be mobile in the rock. So the rock needs to be heated up to the point where those mineral grains can begin to group together. And in addition to textural changes, we also have mineralogical changes. And one thing I want to point out here is that the overall composition, chemical composition of the rock might not change. But because we are adding energy in the form of heat and pressure into the system, we can get recombinations of those chemical elements into different minerals. And generally, the mineralogical differences in a metamorphic rock tell you about the amount of metamorphism that happened and about the amount of heat that was produced at the time of that formation. And we can kind of think of that like Bowen's reaction series in reverse. So remember, Bowen's reaction series is how things cool out of a magma, in what order, with the olivines and the pyroxenes and the hornblende and so on. If you think about slowly heating up a rock, the opposite thing happens. So you start to melt your quartzes and your feldspars and most importantly, your micas early on as a rock is slowly starting to heat up. But then remember, metamorphism is just the process of melting interrupted. So at any given time, there might be the presence of different silicate minerals that like to be solid at that temperature, but nothing that likes to be solid at a lower or higher temperature than that. Okay, and so this is a nice table here where if you have a low grade metamorphic rock, it's going to have a lot of a mineral we call chlorite, which is a type of sheet silicate or mica. And if you see like a lot of chlorite and a lot of muscovite, but not much biotite, garnet, starlite, or selimanite, then you've got a slate. So the slates you have in your kit, the mineralogy there on the surface, that sheen that you see, it's a lot of chlorite and it's a lot of muscovite. Then if you have, chlorite, muscovite, and considerable biotite, you might have a phyllite. If you have no chlorite anymore, but muscovite, biotite, and garnet, you've got a schist, and there'll be some starlite in there too. That's actually very common. Starlite, it's a cool mineral. I'll bust it out and show you guys. And then also selimanite at the very high end. So if you have a rock that's got, mostly garnet and selimanite, then it's a nice, and it almost got to the point where it would start to melt. So let's talk about some of the common metamorphic rocks. These are the metamorphic rocks that are in your kits. And these are the ones that are most commonly found on the surface. And I'm going to show you some examples and talk about their characteristics a little bit, but I also want you to make sure that you do a deep dive when we're in lab and hold these things in your hand and kind of look at them, because you're going to notice things that are going to help you differentiate between them. Again, with the foliation textures, slaty texture produces a slate, and that's a fine-grained foliated rock. So it's lightly foliated, it's fine-grained, but remember it has those like kind of flat, slaty cleavage planes. Again, you have a phyllite, which has a phyllitic texture, and it's got a shiny luster, and it often has these kind of wavy foliations. A schist is strongly foliated, and it has more than 50% of these kind of scaly or platy or elongated minerals. And then a gneiss is a banded metamorphic rock with the separation of the dark and light minerals. So here are examples of that. And let's say, let's take a shale, like a mudstone, and let's start to metamorphose it and then increase the metamorphosis. Wait, metamorphosis, that's probably a biological term. Metamorphism, let's say, of a shale. So when it's lightly metamorphosed, we get that slate, which is this platy, flat surfaced, shiny, more dense than shale metamorphic rock. And that's slate. Then you have phyllite, so it's starting to metamorphose even more. So again, this was a shale, it was a mudstone. Then it became a slate, but pressure and temperature continued, and we get a phyllite. And here in the phyllite, we've got that shiny luster, and it's starting to get a little bit wavier. So not flat like this. You start to get waves on the surface. Then we start to get some of those mica minerals recrystallizing on the edge. So we get kind of pristine micas forming separate from the rest of the rock. And this, I mean, it looks a lot like fish scales sort of on the outside of the rock, and that's your schist. And that's going to have a really high luster. The micas have a high luster generally, but it's usually just kind of messy. Schist is sort of what we call a garbage term in the fact that it's like a big garbage can that we throw lots of things into. So a lot of times you'll walk up to a metamorphic zone, like in an outcrop, and you'll just see this kind of big mess of stuff with lots of micas on the surface, and we call that a schist. But there are different levels of schist. But once you get to the highest metamorphic grade, then you have a nice and you know it's not a sandstone because there aren't sand grains. This isn't a sedimentary rock, even though it has layers. If you look and you see a bunch of pyroxene and a bunch of quartz and a bunch of feldspar and a bunch of mica, but they're in this banded formation here, that's a gneiss. And then for the non-foliated metamorphic rocks, we've got marble, which is metamorphosed limestone. And it's usually made of, it almost looks like a quartz. When quartz is in its really fractured form, not like nice terminated crystals, but that big like mass of just tons of crystal grains. But in this case, it's not made out of silica, it's made out of calcite. And that's because limestone is made out of calcium carbonate. So a marble in its white form also often can look like a nice white quartz, but all you have to do is scratch a little bit onto a streak plate and drop acid on it, and it will fizz. A quartz will not. So speaking of quartz, we also have quartz sandstones that metamorphose into the quartzite, which I talked about a little bit earlier, but that's a metamorphic rock that's just made from those quartzite grains, or those quartz grains in the sandstone, getting fused together into a quartzite. So here's what a quartzite looks like. Sometimes it can even retain some of the layers from the sandstone, and it can have different sedimentary structures in it, like crossbeds or ripple marks. But all those quartz sand grains have been fused together into solid quartz grains. But oftentimes you'll see the textures that we normally see in sandstones. Because remember, there's no tectonic deformation of these rocks. So a lot of those structures were just baked, similar to the way you would bake a clay pot. And so those textures can get sort of baked into place. And some of the oldest crossbeds and ripple marks and mud cracks that we have on the planet are in quartzites, because other sandstones weather away and those things don't get preserved. But metamorphosed sedimentary rocks get preserved, because metamorphosed rocks, like I said, are denser and harder and more resistant to erosion. And then when we have a metamorphosed limestone, we get a marble. And here you can tell it kind of looks like a big massive quartz when it's not in its crystal form, when it's white anyway. But if you look at these grains, sometimes you can see rhombohedral shapes based on the form that calcite takes. But a telltale way here is to just scratch this with a piece of metal or scratch a bit of it onto a streak plate and then drop acid on it. It will fizz slightly. So let's look at what these look like in context. So if we take a basalt, let's say, or an andesite over here, this is a basalt, and it's not metamorphosed at all. This would have just been a a flood basalt that erupted onto the surface at a hot spot or a divergent boundary. And then as we increase metamorphism, we get a schist. And there are different types of schist, and this is based on the amount of chlorite or the amount of biotite or the amount of starolite or any of the minerals that would have crystallized out based on that reverse Bowen's reaction series that I showed you. And if there's a lot of chlorite, you get something called a green schist. Chlorite is a green mica mineral, and it tends to turn this basalt a more greenish color. I have some samples of green schist in the lab from my research area as a grad student, and I can show you what this looks like if you're interested. And then eventually that andesite, once it's past the green schist phase, will become a gneiss. And here we see mostly dark minerals because it started as a dark basalt, right? So mostly it's got dark minerals, but you can still see the folding, especially when hydrothermal fluids move in, because that fold is there in that rock, but we can't see it because there's no difference in color. But eventually some hydrothermal fluid that's got a lot of quartz dissolved in it, it moves through this rock later on and it exploits these folds, and as it cools, it deposits that quartz in there. And so the quartz comes through and sort of like magic ink will show you where those folds were. And then other igneous rocks can also become gneisses. Like, so here's a granite over here, which has a fair amount of fracturing in it. I would say this granite's already, the one in this picture here, is already started to be altered through some kind of tectonic process. But if you squeeze it enough, you'll get this nice banded gneiss here. And what's happening here is these quartz grains and hornblends over here separate out, and so you just get bands of quartz and bands of hornblende. And where do you think the stress from this was coming from? Well, as we know, it's always perpendicular to the bands, so the stress would be coming from the top or the bottom relative to the bands when this was forming. So here's what those metamorphic environments looked like. So if you have a contact metamorphism, you'll have a magma chamber here, and it's intruding up into some sedimentary units. It's maybe even erupting up and popping out on the surface as a volcano. And so it has some fractures and stuff in it associated, and some faults associated with the volcanism there. But what's happening around the magma chamber is along this zone of alteration, which we call the areola, you have a metamorphic areola forming where that magma chamber is heating up both the country rock or host rock, which is the sedimentary layers, but also the fluids contained in those layers, wherever there's water. And so that water is going to move through the areas or the sedimentary layers closest to the magma chamber while it's still hot, and it's going to alter into this metamorphic areola that we see here. And contact metamorphism is controlled by obviously the size of the magma body, how much surface area of the magma body is there. The mineral composition of the host rock, so what types of minerals did we find in a given sandstone or a given mudstone? And then, of course, the availability of the water, the hydrothermal fluids that are in that rock. A dry, dehydrated sandstone that's very deep won't be as metamorphosed as a sandstone higher up in contact with a magma body, because there'll be more water available for that magma body to heat up. And the dominant metamorphic agents in contact metamorphism are heat and chemically active fluids, right? And so no tectonics, or very, very slight tectonics. And that gives us those non-foliated hard rocks like quartzite and marble. Then we have regional metamorphism. So this is when mountains formed, so rocks are being squeezed and folded. And they have so the dominant metamorphic agents here are heat and pressure. And regional metamorphosed rocks can be low to high grade, so slate to gneiss. And the change in intensity is reflected in the changes in the textures that we see, like the foliation textures and whatnot. So if we were looking at a mountain belt, where would we expect to see these metamorphic rocks? So at the very core of the mountain belt, down here, you've got some magmatism, maybe even, because it's so hot and under so much pressure down there. But these rocks are going to be so squeezed from both directions that you'll get a gneiss. So the most highly metamorphosed rock you can get. Then as you move away, so further away, less pressure, but still real deep and real hot, that's how you get a schist. Then as we move further away from the zone, you get a phyllite, and then the furthest away, you get a slate. And you'll notice here in this diagram, we've got subduction happening, but we've got continent to continent starting to form here. So not to harken back to 2 weeks ago, gosh, that feels like forever ago, this subduction is eventually going to stop, right? And we're just going to get continent to continent here. So none of these rocks are as a result of the volcanism that would happen further down in the subduction zone. Those would be volcanoes over here off frame that we can't see. So these aren't volcanic in any way. They're metamorphic and being heated up, but they have to melt all the way to become part of a volcanic system. So here's a phase diagram. Geologists love phase diagrams. This is how rocks or minerals change over different temperature and pressure parameters. And if you look up here at the top, if we have country rock, let's say a sedimentary rock, or an igneous rock, or even another metamorphic rock, to be honest, that's being heated by just the contact metamorphism from a magma chamber, you'll see that at low temperatures and pressures, we have no change, which we would expect. And then as you increase temperature, you'll get a slate, and then a phyllite, and then a schist, and then a gneiss. And then eventually, if you heat it up enough, you pass the solidus, or the solid melting boundary. And if you get large portions of that rock to melt, but not the whole rock melting, you can get big hunks of recrystallized, cooled igneous rock in a metamorphic rock. So a lot of times in a gneiss that's really, really, really banded, that's been heated up really high, sections of that will start to melt out quartz and feldspar, and then that process gets stopped. And so you have remnants of the metamorphic rock, the gneiss, still left over, but then you have big chunks of igneous rock, like a granite, in that. We call that a magmatite. And I'll show you a version of that. We have a nice, beautiful sample of that in the lab. And that's at these temperatures, right? But if you start to add pressure down here at the bottom, there's no such thing in nature as high pressure, low temperature in rocks. It's not found in nature. We can do it in a pressure chamber, like on the surface, but in nature that simply doesn't happen. As you go down in depth, you increase in temperature. That's just the way it is. And so, at high pressures and low temperatures, we don't see anything that exists like that. But then we start to get a slate being produced, and a phyllite, and a schist, etc. What I think is important about this diagram is that pressure is a control on temperature, as in it's a control on the partial melting and recrystallizing of the different minerals required to make a slate, or to make a phyllite, or to make a schist. Okay, so you could have increasing temperature, but if that rock is at some considerable depth, it doesn't metamorphose until it gets high enough in temperature. Then it will start to form a slate. Then it'll start to form a phyllite. So notice, if we were down here, if we were at this pressure, right? So this is a definite depth in the crust. Things have to heat up quite a bit in the rock before we get to a metamorphic rock. And when we do, we jump right to a gneiss. So that's why gneisses are formed very, very deep in the earth and not slates, let's say. Slates like to form at lower pressures and at certain temperatures. And if a rock is deep and at this temperature here, it'll start to form a slate. Whereas if it's at a higher depth, or a lower depth or a higher level in the crust, it takes more heat to get it to a slate. So hopefully that makes sense. If not, hit me up in the virtual classroom thread, or shoot me an email, or mention it in the discussion threads if you'd like some more explanation about this. So here we're getting the contact metamorphism. Down here we start to get the regional metamorphism. And then at the very low depths, that's when we get the subduction related metamorphism. So where in the crust do we see those types of temperature and pressure conditions? So here's a subduction zone. It's a convergent boundary. Way down here, we would have high pressure and high temperature. But up top, I want you to look at how we can get kind of weird ones like high pressure, low temperature, and high temperature, low pressure. So in a subduction zone, right at the subducting boundary here between the oceanic plate and the continental plate, we can get areas where there's lots of pressure being exerted on these rocks here, but they're higher up, so they're lower temperature, okay? Because you have to, in order to heat up a rock by temperature alone, you either need magma around or you need to be deep, closer to the mantle, where it's just hotter. So here we have high pressure, low temperature, okay? Then, on the continental plate, you can have magmatism happening from the subducting slab, like we've talked about with volcanism, where volatiles flash melt parts of that crust, and it rises up and it gets stuck in the crust. And when that happens, you get high temperature and low pressure. So this is your contact metamorphism here, right? Then you can move over here where we have additional high pressure and low temperature, but some amount of hotter hydrothermal materials moving into this zone here where we've got a bunch of thrust faults, right? And this is where the hang wall is thrusting up above the foot wall. And in those zones, we can get high temperature and low pressure and high temperature and high pressure metamorphic rocks. So all, like, really in these thrust belts, you can get slates, you can get phyllites, you can get gneisses, and you can get schists. And then, that's also where we see shear zones and things like that. So this is where we get regional metamorphism here, and then right here is where we would get contact metamorphism. And in like I sort of zoom in to that thrust zone there. This is kind of what you see when you do a cross section, and you can see these thrusting sheets here. You can see cleavage and shear zones here. You get some regional metamorphism here with the shearing here. And so along this whole boundary, in between these different hunks of material, you get metamorphism at all these boundaries here, right? And that's in a convergent thrust zone. And then at divergent boundaries is we also see contact metamorphism, but not so much regional metamorphism, because regional metamorphism happens when there's pressure, right? Stress. Here we don't have any compressional stresses because the plates are moving apart. And that upwelling magma that comes in and creates new seafloor up here at the top, when it's sitting down here in a magma body, it's heating up seawater and other hydrothermal fluids, and it's contact metamorphosing this basalt in this case. And on a continental rift, we see that. This is like Iceland or East Africa. We see asthenosphere magmas moving up into the crust, and superheating those hydrothermal fluids there, and those fluids are moving out and metamorphosing that rock. And the same in seafloor spreading. We have normal faults here, and then we're getting metamorphism of oceanic crust here. Whereas over here, we can get metamorphosing of continental crust. So that's metamorphic rocks. I thought you guys would get off easy with only 32 slides, but this is my favorite, and I talked a little bit more than a minute per slide like I had planned. So anyway, hopefully that all made sense to you, and hopefully you can see that metamorphic rocks really are telling us something about process, and it's not so much about what they're made of, but you know, how dented their fenders are. So next we'll continue with mineral and energy resources. So we're pretty much done now with the rock types and rock identification, and definitely take a look at these in lab and take a look at how they're similar and how they're different to the other rocks that you have in your kit, like igneous rocks and sedimentary rocks, because you have to be able to notice how things are different as much as how they're the same, to try to suss out the differences between the different rock types. So I'll see you in the upcoming lab, and I hope you have a great day.